Hi, welcome. This is chapter 17, alcohols and phenols. And basically here what we will explain is how we can name the alcohols and phenols, the properties of alcohols and phenols, preparation of alcohols, a review, and finally we will see several reactions of alcohols. Okay, importantly, an alcohol is basically OH that is bonded to a carbon sp3, like you can see here, and a phenol is a hydroxyl group, a alcohol, that is bonded to an aromatic ring. Please don't confuse when an alcohol is bonded to a single double bond. Okay, because then it's an enol, and the properties of enols are very different than not alcohols or phenols. If we check how we can synthesize the two most common alcohols in the industry, basically to get methanol, what we can get is the hydrogenation of carbon monoxide, as you can see here, using as catalyst a zinc, at high temperature obtaining the methanol. In the case of ethanol, basically the most common way is we take ethylene, we add water in acid media, normally phosphoric acid, and what we get is the ethanol. Phenols and alcohols are present in a lot of different natural products and medicines, and probably one of the most common medicines that we have a phenol derivative is the aspirin. Okay, how we can name the alcohols? Basically, in the naming of alcohols, we have to use a similar method that we used it until now. The first, we have to identify the main chain. The main chain is the longest carbon chain that contains the major number of alcohols. Okay? That means if, for example, we have this compound, OH here, another OH here, and here a long chain of carbons, the main chain will be the chain that contains the two alcohols, despite that this other chain contains more carbons. We have to take the longest carbon chain that contains the major number of alcohols. Okay, and then what we do is to name this carbon chain using the same system that we used in the last chapter, for example, methane, ethane, propane, butane, etc. And we remove the E at the end, and we put the termination ol. The termination ol identifies that our compound is an alcohol, and the alcohol is the major functional group. If an alcohol is not the major functional group, as we see in the next lectures, then we can use it as substituent, and then will be with the name hydroxy. Will work like, for example, a halogen. We will put where is the position of the alcohol, followed by hydroxy. Okay, but to cite alcohols as a major group, as a main functional group, we will put the name of the longest chain followed by ol. Then we have to number the major chain like we did in the other chapters, and we have to start the numeration by the site where we obtain the lower number possible for the alcohols. Okay, and finally we name the substituents according to the position in this chain. We put the name of the substituent with the number of the position where is the substituent. Okay? Let's put an example. Here we have a 5 carbon alcohol. The main chain is a 5 carbon. Okay, and then I start numbering by this side. Why? Because the alcohol is in position 2. If I start by the other side, will be in position 4. Okay, then, if it's 5-member ring, will be a pentane. I remove the E, and I add ol. And where is the alcohol? In position 2. And here I have two possibilities. I can say that it's 2-pentanol, or I can say that it's pentan 2-ol. I can put the number just before ol, or just at the beginning of the name of the main chain. It's up to you. The new UPAC rules are following the number in the middle, but we accept, and we will accept in the exam, any of the two possibilities. And then what I need to do is to name the substituents. Here I only have one substituent, that is this methyl compound that is in position 2. That means that this will be a 2-methyl 2-pentanol or 2-methyl pentane 2-ol. Okay? The next one, what we have here is the main chain will be the cyclohexane. Okay? That means that this will be a 1,4-cyclohexanol. Remember that when we have a ring where we have the functional group will be position number 1. If the alcohol is position number 1, the other alcohol will be position number 4. That means 1,4-cyclohexane diol. Why di? Because we have 2 alcohols. If we have 3, will be cri. If we have 4, tetra, etc., etc., etc. Okay? And the last thing that I have to do is to give the stereochemical information. In this case, the 2 alcohols are in the same direction of the ring. That means both are up. That means that this will be a cis 1,4-cyclohexanediol or a cis cyclohexane 1,4-diol. Up to you. Last one. Here the main chain will be this one. And I start numbering from here because then the alcohol is position 2. If I start by the other side, will be position 4. Again, this is 4 carbons, that means butane, and the alcohol is in position 2. That means that it will be butane 2-ol. Okay? And then the only that I need to do is to name the substituent, that is this phenyl ring, that is in position 3. That means that the name will be free phenyl 2-pentanol or free phenyl pentane 2-ol. Okay, as in other functional groups that we studied, there are some alcohols that has a common name. Instead of the UPAC name, the people use a common name, like for example, this is a benzyl alcohol. Okay, this is allylic alcohol. This is terbutanol or terbutyl alcohol, up to you. This is ethylene glycol, and this is glycerol. Okay? Importantly, when we have an aromatic alcohol, what we need to do is to cite the name of all this compound is phenol. Okay? That means if we have this compound, all of this is phenol. That means that we have a substituent here that is a methyl, will be 3-methyl phenol, because 3, the hydroxy will position 1, this 2, this 3. Okay? Remember that we always have to choose the lower numeration possible. That means this will be 3-methyl phenol. Or, if you remember how we can say what we can name the aromatic compounds to, will be a meta, because it's 1 free, meta-methyl phenol. Here the next. Again, we have a phenol, and then we have 2 substituents that are 2 nitro groups that are in position 2 and position 4. This will be 2,4-dinitrophenol. Okay, let's do the problem 17.1. We start from the first. The main chain will be this. That is the one that contains the 2 alcohols and is the major chain in carbons. This is 1, 2, 3, 4, 5, 6, is 6, will be hexane, okay, and then we have 2 alcohols in position 2 and 4, if I start counting from here, because if I start from the other side, will be a bigger number. That means hexane 2,4-diol or 2,4-hexanediol, sorry, again, will be hexane because it's a 6-member ring. Then we have 2 alcohols in position 2 or 4 will be hexane 2,4-diol or 2,4-hexanediol. Okay, and then the rest is to add the substituent. The substituent is this methyl that is in position 5. This will be 5-methyl 2,4-hexanediol or 5-methyl hexane 2,4-diol. Okay, next one, B, If we check the major chain, will be, for example, this. Okay, we have a four carbon chain. Okay, that means that will be butane. Where is the alcohol? The alcohol is in position 2, because I have to start from here in order to give the lower number possible. Okay, and then will be butane 2-ol or 2-butanol. And then I have to add the substituents. In the 2 positions I have methyl, and in the 4th position I have a phenyl. That means that will be 2-methyl, 4-phenyl, butane 2-ol, or 2-methyl, 4-phenyl, 2-butanol. Remember that the phenyl and the methyl are 2 substituents. We have to put in alphabetical order when we write it. Okay? Good. Then we go for the compound C. Compound C is a cyclohexanol. The major carbon chain will be the cycle. That means it's a cyclohexanol. And then in position 4, remember that always in a cycle the hydroxyl or the main group will be position 1. In position 4 we have 2 methyls. That means this will be 4,4-dimethyl cyclohexanol. Okay? Next one, D, we have this beautiful cyclopentanol. Okay? Again, the position of the OH will be position 1, and then the bromide will be position 2 in order to have the lower numeration. In this case will be 2-bromo cyclopentanol. Okay? But here what we need to add more is the stereochemical information. If you see, the OH is going up, is going towards us, while the bromide is going to behind the slide. That means are in opposite directions. This will be a trans 2-bromo cyclohexanol. Okay, E. In the E we have an aromatic alcohol. Remember, aromatic alcohol, this is a phenol, and then we cite the substituents. The substituent we have in position 3, remember alcohol is 1, 2, 3, we have a methyl, and in position 4 we have a bromo. That means this will be 4-bromo, 3-methyl phenol. Okay, remember that the bromo is B. That means that in alphabetical order is always before than not the methyl. And the last one, okay, we have a 5-member ring as a main group. That means will be a cyclopentanol. However, we have a double bond in the ring. That means that this will be a cyclopentane. And we have to put in which position is the double bond. That means this is 1, this is 2, is in position 2. That means will be a cyclopent2-n-ol. Okay? Cyclopent2-n-ol. Okay? My advice, do it with calm. Try to do it step by step, and you will see that it's quite easy. Okay? What are the properties of the alcohols and phenols? Well, basically the main property of the alcohols and phenols is done by his functional group. We have a carbon bonded to a OH. That means this carbon, because it's bonded to an H, to an oxygen, that the oxygen is more electronegative than not the carbon, here we will have a density positive charge, while in the oxygen we will have a density negative charge. That means these molecules are polar. Moreover, because we have a hydrogen bonded to a very electronegative atom, in this case the oxygen, this hydrogen becomes acidic. That means that we have hydrogen bonding too. Okay? Because this proton is acidic, what we can do is basically propose the acid reaction. That means the dissociation of alcohols. Okay, alcohols are weakly acidic. Okay, and the pK is around 16, 18, this type of pKs. Okay? Always, phenols will be more acidic by far than not normal alcohols, alcohols sp3. Why? Because when we have a phenol, the conjugate base, this compound, the negative charge can be stabilized by resonance form. We can put this negative charge here, and then move these 2 electrons here. Because we can do this, we stabilize this form, making this reaction going to the products, so more acidic. Okay, we can define the constant of the equilibrium of these acid reactions, like in the same way that we defined the constant of equilibrium for acids, and will be the multiplication of the concentration of the products divided by the concentration of the starting materials. And then normally when we are using acids, as you will remember, what we can use is the pK value. The pK value is not any more than the minus logarithm of the equilibrium constant. Okay? Then, how can affect the different substituents or the morphology, the construction of the alcohol? Okay, we can have aesthetic effects. Okay, that means in order to be acidic, this proton has to be able to be attacked or to be trapped by a base, isn't it? That means that the base has to arrive to the proton. When bigger is, when more hindered is this alcohol, more difficult will be that the base take the proton. That means here you have the methanol, the pKa is around 16, while in the terbutoxide, the terbutyl alcohol, the pKa is around 18. That means when more hindered, less acidic. Okay? But if you check the two pK, the difference is not so big. What could be a very big difference is when we are using electron withdrawn atoms in the carbon chain of the alcohol. Here you have an example. We have here a carbon that is surrounded by 3 trifluoromethyl groups, okay, versus the terbutanol or terbutoxide without fluorines. Okay. Check that the pK of the fluorines is by far lower than not the pK of the terbutanol. Okay. Why? Because when we have a very negative atom, a very electronegative atom in the carbon chain, this stabilizes the negative charge of the oxygen, okay, by inductive effects. That means that when more electronegative atoms we have in the alcohol, in the carbon chain of the alcohol, more acidic will be this alcohol. And it's important the number of electronegative atoms, but also it's important where are these electronegative atoms. That means when closer are to the oxygen of the alcohol, more effect will have. Okay, that means this compound this alcohol and this alcohol okay, the first one has the fluorine 2 carbons away of the alcohol, and the second one has the 2 fluorines near to the carbon that is close to the alcohol. Okay, the second one will be by far more acidic because the electronegative atoms are closer to the oxygen, by inductive effect will be more effective. Okay? Good, then the alcohols, if we are talking about his synthesis or reactions, are very, very, very useful in synthetic chemistry. Basically, we can synthesize an alcohol for a plethora of different starting materials like alkyl halides, esters, carboxylic groups, carboxylic acids, alkanes, ketones, aldehydes, or ethers. Okay, and probably the most common and the most used ways to synthesize alcohols is some that we already did. That is the formation of an alcohol from an alkene. Remember, we have two typical ways to transform an alkene to an alcohol: a hydroboration and solvomercuriation. Okay? Remember the hydroboration, we add BH3, borane, to the double bond. The boro is always added to the less substituted carbon, as you can see here in the intermediate. Okay, that means that the hydrogen is going to the most substituted carbon. Both boron and hydrogen are coming from the same site. This is important. And then in the next step we add hydrogen peroxide. the hydrogen peroxide will change this boron for an alcohol keeping the same configuration. That means check that in the final compound the OH and the hydrogen that we add thanks to the borane are in the same site. Okay? That means in this case we will get a trans 2-methyl cyclohexanol. However, if we do the solvomercuriation, we are using mercurium acetate. Okay, remember we first form the free member ring with the mercurium, and then the solvent of the reaction, in this case water, is opening this free member ring, and the OH is attacking the most substituted carbon. Why? Because it's the carbon that stabilizes better the positive charge. Okay, and the attack of the hydroxyl group is from the opposite side where we have the mercurium getting this intermediate. Once we have this intermediate, we add sodium borohydride and we change this mercurium for a hydrogen, and we get the final compound. That means with borane we get the hydroxyl group in the less substituted position. With mercurium acetate we get the hydroxyl group in the most substituted position. Okay, for example, we can do these two exercises. In the first one we have this compound and we add borane. The first step will be the addition of borane. Remember, the borane will be added here and the double bond will be removed. Okay, and then we change the borane with the OH when we add hydrogen peroxide and we get this compound. Okay? Right? Remember that the OH will be in the less substituted carbon for the reasons that we said in the other chapter. If we do the same with mercurium, well, the same not with the compound number B, what we get is we add the mercurium, okay, and the first step will be the formation of this compound without the double bond. Okay, the free member ring with the positively charged. Then, as we are using water as a solvent, this water will attack the most substituted position, and what we have is this compound. Okay, and then when we add the sodium borohydride, what we will get is the change of the mercurium for a hydrogen, as you can see here. Okay? Then another thing that we can do is to transform alcohols into alkyl halides. How we will do it? Well, one method, if we have a tertiary alcohol, is to use a hydrochloric acid or hydrobromic acid, a hydrogen chloride or a hydrogen bromide. Okay? What is happening? First step, we remember that the hydroxyl groups are very bad leaving groups. That means we have to transform this OH in a good leaving group. How we do this? Basically, we protonate the OH, and now the leaving group is water. That is very good. The leaving group is departing, and we form the carbocation intermediate. Okay? Now you can understand why you need to use tertiary alcohol, because we have to stabilize this carbocation, and the best stabilization is with tertiary carbons. When we have this carbocation, then the nucleophile, in this case the chloride or the bromide, depending on which acid we use, is attacking, and we form the final tertiary chloride or bromide. Okay? If we want to use primary or secondary alcohols, what we need to use is, in the case of that we want to add a chloride, is thionyl chloride, that is this compound, SOCl2. Then the alcohol attacks the sulfur, forming this intermediate, and departing a chloride, and then the chloride is attacking through a SN2 to form the final alkyl chloride with inversion of configuration. Okay? And now you have the reason why it's working only with primary and secondary alcohols, because the reaction is going through a SN2. If we are using a tertiary, simple, the nucleophile cannot arrive to do the SN2, for the reason that we explained in the chapter of substitutions. If we want to put a bromide, we use a similar reaction, but in this case using phosphorus bromide. Okay? Then the oxygen attacks the phosphorus, forming this intermediate, and departing a bromide. The bromide is attacking through SN2. This is the leaving group, and we generate the alkyl bromide again with inversion of configuration, because remember, it's a SN2, okay? And for the same reason than before, has to be a primary or secondary. We cannot do it with tertiaries, because if not, we know that tertiaries didn't work with SN2s. Okay? Thank you very much for your attention. Remember, you have the study questions from the book and the reading assignment, that is the textbook, chapter 17, points 1, 2, 3, and 6. Okay, thank you very much for your attention, and see you in the next lecture.